Welcome everyone. The purpose for this video series is electrochemistry, and this specific video we're going to talk about redox chemistry and oxidation numbers. So an oxidation number is an assessment of how an electronic environment of atoms in a compound is different in comparison to the atom of the pure element, right? So how does that atom's electronic environment look when it's in a compound versus when it's by itself in its pure elemental state. Now, when we look at oxidation number notation, we are going to reverse the sign compared to the way that we do it with charges. So when we write charges, it always goes the number and then the sign, but when we look at oxidation numbers, we're going to flip that and put the sign first and the number second. When we're determining the oxidation number for an element, there's a list of rules, and the first one is based on the definition, right? So we said in comparison to an element in its pure state. And so if an atom is in an elemental state, then we're going to say that the oxidation number is 0. If it is a monoatomic ion, so if it's in an ionic compound, for example, and you've got a monoatomic ion, the oxidation state is going to be equal to the charge. And then the rest of them were mostly focused on the nonmetals, looking at those oxidation numbers. Hydrogen will usually be a +1 for the purposes of this class. You have the rare occasion if hydrogen is attached to a metal, then it will have a -1 charge. Oxygen, most of the time, will be a -2, except when you see it in hydrogen peroxide, then it would be a -1. And then halogens are always going to be -1, except when they're combined with either oxygen or another halogen. And then you would determine it based on the fact that oxygen should be a -2, and then you could calculate the oxidation state for that halogen. And then the sum of the oxidation numbers for all atoms in a molecule or a polyatomic ion has to equal the charge on that ion. And if, of course, there isn't a charge written, then we assume that the charge on the molecule is 0, and so all of those oxidation numbers for all the atoms should add up to 0. So let's look at some examples. In the first example, we have potassium nitrite. And the first step is to break it up into its ions, because this is an ionic compound. And so this will split up into potassium and your nitrite ion. And potassium being in group 1, we know that the charge on that is a +1. And on the nitrite ion, that would be a -1. Okay, so we've got to find the oxidation number for all the elements in this compound. So we need it for potassium, nitrogen, and oxygen. And if you have a monoatomic ion, like potassium here, then the oxidation number is simply going to be equal to the charge. And so we have a +1 oxidation number. And then oxygen, remember, is almost always -2 unless it's in hydrogen peroxide. And so we know the oxidation number for oxygen is a -2. So the only one we have to calculate is the nitrogen, and that's where we look at the overall charge of the polyatomic ion and say that all of the nonmetals, all of those oxidation numbers have to add up to that charge of a -1. So I have one nitrogen atom in the polyatomic ion, and I have 2 oxygen atoms in that polyatomic ion, and the overall charge is a -1. Now I know that the oxidation number for oxygen is a -2, right? I've already determined that based on the rules, and so I can plug that in for the oxidation number of oxygen here. So the oxidation number for nitrogen we do not know, but we know for oxygen it's a -2. And then overall that gives me -1. And so of course we can calculate this. Nitrogen minus 4 equals a -1, and so the oxidation number for nitrogen must be a +3. And you can always go back and plug that into the equation and make sure if you have nitrogen, which is a +3, plus 2 times your oxygen of a -2, of course that should come out to be -1 for that charge on the polyatomic ion. Okay, so let's do another example. We've got H2PO4 negative. So all of these are nonmetals, and combined they're giving you a polyatomic ion. So we're going to look at the nonmetals that we do know. And we've got hydrogen. Let's see. Hydrogen, phosphorus, and oxygen are the three that we've got to figure out. Hydrogen, when it's bonded with nonmetals, is going to be a +1. Remember, it's very rare for it to be a -1. It would have to be attached to a metal. And we know oxygen is a -2. Okay, so we can plug those into the equation where all the atoms have to add up to the charge on the polyatomic ion. And so we have 2 hydrogens plus a phosphorus plus 4 oxygen atoms has to equal the overall charge on the polyatomic of a -1. We know the oxidation number for hydrogen and for oxygen, so 2 times a +1 plus phosphorus plus 4 times a -2 for that oxygen oxidation state. And we can solve this. We get 2 plus phosphorus minus 8 equals -1, and so we'll find that phosphorus is a +5 charge. Okay, and again, you could plug that back into the original equation and just make sure that that comes out to be -1. So this is a little bit of review, hopefully from Gen Chem 1, oxidation versus reduction. You could have memorized one of 2 phrases. Oil rig is one, or Leo the lion goes grr, maybe another one that you know. So oil oxidation is loss of electrons, and rig reduction is gain of electrons. So if you are the species that is reduced, that means that you are the oxidizing agent. Okay, and remember, for you to be reduced, your oxygen number has to be reduced or has to decrease. And then if you're oxidized, you are what we call the reducing agent because you're reducing something else, and so that makes you the agent. Okay. So we're going to look at some examples now with the whole reaction and ask what is oxidized, what is reduced, what's your oxidizing agent, your reducing agent, and what is the oxidation state on the reactant side and the product side for each element. And so we're going to list this out just like we did before and similar to the way we would for a balanced chemical equation. If we're trying to balance an equation, we're going to list out the elements in order that we see them on the reactant side. And we're going to list the oxidation number on the reactant side and then put an arrow and list the oxidation number for the product side. So remember, if something is by itself without a charge, it's considered to be in its elemental state. And so magnesium here, it's not attached to any other element, and so its oxidation state is 0. Okay. Now nickel and chloride, those are in a compound, and we can break that up into its ions. And so we get nickel plus 2 chloride ions. Now we know the charge on a chloride ion is a -1, and since there's 2 of them, that's an overall -2 charge coming from the chlorides, and so that means that the nickel has to be a 2+ charge. Okay, and these are both considered monoatomic ions, and so the oxidation state is equal to the charge of the ion, right? So nickel would be a 2+, and chloride, oh sorry, we're talking about oxidation numbers, so that should be a +2 and chloride would be a -1. Now remember, we're not talking about the whole charge from all of the chloride ions, right? That would be a 2 negative charge. We just want the charge on a single chloride ion, and so that's why we're writing down -1 for the oxidation state. Now on the product side, the nickel is now by itself and it's not combined with anything else, and so this oxidation state will be 0. And then the magnesium is now in a compound, right? This is a single replacement reaction where the nickel has, or the magnesium has replaced the nickel. So the compound magnesium chloride, again, magnesium is in the group 2 on the periodic table, and so we know it's going to have a 2 positive charge. And the chloride ion stays the same with a -1. So the oxidation state for chloride is a -1, and for magnesium it's a +2. Okay, so we can see that the chloride ion, the oxidation number is not changing, right? It's going from -1 to -1. And so we can ignore that. It is neither, it's not oxidized or reduced. And then the two we have left, I like to look for the one that's being reduced first, and that would be the nickel, because it's going from a +2 down to 0, and so that oxidation state is reduced. And once I determine that, that means that the magnesium must be oxidized, and we can see that it's going from 0 to a +2. And then whatever is oxidized, that has to be your reducing agent, right? So they're opposite. And that is because it is reducing the nickel, and the nickel is oxidizing the magnesium. And so nickel would be your oxidizing agent. Okay, let's do one more example. This time we're looking at a combustion reaction, combustion of ethene, and so there's not any metals present. We're dealing with all non-metals. We've got carbon, hydrogen, and oxygen. Okay, remember that if hydrogen is in a compound, it's typically going to be a +1, especially since all of these are non-metals. Oxygen will be a -2 if it's in a compound. So hydrogen is in a compound with carbon, and so it does have a +1 oxidation state on the reactant side. Now oxygen, even though there are 2 atoms, it's still bounded only to itself, and so we call that a molecular element. Okay, so it's not considered to be in a compound. It is by itself without a charge, and so the oxidation state on oxygen on the reactant side should be 0. And so we've only got to figure out the carbon, and remember we can write out the equation. We've got 2 carbons plus 4 hydrogens, and then overall, if there's not a charge shown, then it must be 0. We know the oxidation number for the hydrogen is a +1, so we've got 2 carbons plus 4 times a +1 oxidation state equals 0, and so we can find that carbon should have an oxidation state of -2. Okay, and then we look on the product side for all 3. And on the product side, everything is in a compound, right? We've got carbon dioxide and water. And so our hydrogen and our oxygen, we know. Hydrogen will still be a +1 in a compound. And oxygen, because there's not peroxide present, that's going to be -2. And so the only thing we've got to figure out is that carbon, and we've got the CO2. Notice how I don't care about the coefficients. That's not important here. So I just need carbon plus 2 oxygens has to give me an overall charge of 0. And I know the oxidation state on oxygen is a -2, and so carbon plus 2 times a -2, and solve to find that carbon is equal to a +4. And this makes sense because carbon and hydrogen are very similar in electronegativities, but carbon is slightly more electronegative. And so when it's bound with a hydrogen, it's going to have an oxidation state that is negative. And then when it's bound with oxygen, oxygen is a very electronegative element, which means that carbon will become electropositive in comparison. Okay, and so that's why you see that oxidation state getting more positive. So when we look at what's oxidized and reduced, the hydrogen is not changing, so we can mark that out. That leaves carbon and oxygen. Look for the one that's being reduced, and that is oxygen. It's going from 0 to -2. So that is reduced, which means that carbon has to be oxidized. And of course, whatever is oxidized is the reducing agent. And whatever is reduced becomes the oxidizing agent. And that is kind of where we get the term from. Oxidizing agent comes from the fact that oxygen gas is an oxidizing agent, and it was one of the first ones that we knew about. So we're going to go ahead and stop this video here. In the next video set, we will look further at redox chemistry and looking at balancing redox equations with the half reaction method.